out to the ZT. Well, the T is temperature, and Z is represented by these three transport properties: the Seebeck coefficient, electrical resistivity, and thermal conductivity. And again, just simply, just as solar panels produce electricity when in sunlight, thermoelectric modules can produce electricity when in a temperature gradient. So why use thermoelectrics? And by the way, thermoelectrics can not only be used in power generation, but they also can be used as solid state heat pumps. And so you can do solid state cooling, heating, and power generation. They're small, lightweight, reliable, and rugged. There is electrically powered with few or no moving parts. So that's sort of why we use thermoelectrics. In terms of the thermoelectric power generation products in the market today, excuse me. This is just showing a few of those, from the remote power made by Global Thermoelectric to the radioisotope thermoelectric generators that have historically been made by NASA, to camping stoves from BioLite, and then Alphabet Energy. This was one big thermoelectric generator within a shipping container. And it was made up of these power modules, which again included the hot side heat exchangers and the cold side heat exchangers. They comprised multiple power cards and directly accepted exhaust gas from 350 to 600 C and transformed it into power. And it was connected to the engine exhaust and to the cooling systems. The power cards, which are made up of many power blocks, as you can see here, these are the power blocks that go into the power cards. This had a more rigid substrate on the hot side and a more flexible substrate on the cold side in order to accommodate some of the thermal expansion that was talked about earlier today. And so allowing for some of those thermal expansion differences. So that's what that could do. Now, how are the power blocks made? And again, some of this has already been talked about here today, but for those online, we basically, and in this case, the power blocks that we were making were made out of tetrahedrite material as well as magnesium silicide. In this case, we have the magnesium silicide powder, which we used ball mills for mixing, grinding, and reacting the materials. Those then went into a furnace, and you ended up with chunks or ingots that are solid but not dense. And then they're ground up again within the ball mill, and you end up with the powder again, but this time it's powder of the thermoelectric material instead of the raw elements. So then that material is then hot pressed to make dense ingots. This is a big SPS and hot press. And this I wanted to sort of focus on. We then were able to make large ingots, in this case the tetrahedrite up to 5 inches in diameter, 1 inch thick, and the magnesium silicide stannide was 8 centimeters in diameter, 2.7 centimeters thick. So that's where we were trying to get to in terms of scale. Once you have those ingots, you slice the ingots into wafers, you polish the wafers, you then metallize the wafers, and you dice the wafers into the power blocks or the legs. This sort of summarizes that whole process, going from the raw materials to ingots to power blocks to the device. And again, you can see that here as we described. So I show you that as sort of the initial introduction to all that goes into making thermoelectric materials and devices and putting them into applications. Now I'm going to kind of try to talk about the challenges. I've listed a bunch of the challenges here. This is not an exhaustive list, and I'm not going to be able to, in the time we have today, go into detail about all of the things on this list. But there are many challenges, accurate and effective modeling, and that actually could be at the material level, at the device level, at the system level. You obviously need to have high-performing TE materials, both P and N type materials. They need to be stable. There is thermal expansion management, and oftentimes this requires compression, as many of these materials don't like ending up in tension, and so there is a level of compression that is needed in order to prevent them from being damaged once they heat up and expand. Many of these materials have sublimation or oxidation issues, particularly at higher temperatures. And therefore, prevention methods are needed to suppress those. Once you've built the materials and put them into devices, effective heat exchangers are needed on both hot and cold sides of the device, and effective thermal interface materials are also needed in order to connect those devices to those heat exchangers, all of which require low contact resistance, and this includes also at the T material side, both on the P and the N type materials. And then we even need effective device and system design. And I just mentioned here, including power electronics, these devices produce a particular voltage, a particular current. If you have a dynamic heat source, you may have variable output. And so there's often been a need for having, if you require DC power, you might need a DC to DC converter, or if AC power, a DC to AC inverter, as thermoelectrics produce DC power. It's listed toward the end here, but it may be one of the most important. Obviously, the cost effectiveness is very important, and obviously sustainable and non-toxic materials. So I'm now going to go through and talk about, again, some of my experiences, and in the process of that, really we'll be discussing some of the challenges that came up, but also some of the successes that were had. So in terms of a cost-effective TEG design, the traditional design is what is often called a Stonehenge design or a pie-shaped design, where you have a P leg and an N leg. And here in Madrid, we've talked about this earlier today. We looked at, this is now at Gentherm as opposed to at Alphabet Energy. We looked at an alternative design, and this says BSST. BSST is a precursor to Gentherm. But in this design, we stacked up the thermoelectric materials in sort of we call this the T or Y-shaped design. And this was an interesting design from the standpoint, for one, if you have a different P and N type materials, they will expand potentially differently when they're heated up, causing potential problem where you could have damage to the part. In this kind of a configuration, you don't have that issue because they're expanding in a different plane compared to the heat. Also, this can be a good design in terms of if your legs are not all the same length, and this can accommodate for that. And so we found that this was a pretty useful design. Here is an example of such a part that was made. In this case, the material is bismuth telluride, and you can see that you have the P-type material and the N-type material, and you can see just for scale. This particular part was then integrated into a device, so this is just one particular way we were combating some of the challenges. Another was to make a cylindrical device. And looking at this may be a little bit complicated to sort of see. But in this case, it still uses that T-shaped design that I was just showing you on the previous slide. This is the T part that's on the hot side, and it is contacting these fins. This is the exhaust gas goes into this part here, and this is a bypass, and I'll explain that in a moment. But the bypass here is in the center, and these fins are also, so the exhaust gas can either go through the bypass or go through these fins. And then you have on the cold side, you have coming in through here and going out on this side, and there were tubes that surrounded the outside of this, this part. And these pink parts are P material, the yellow parts are the N-type material, and these surrounded, I'll show you on the following slides. This is an example of the part that we built, and you can see the bypass here in the center with the fins going around on the outside. Why did we need the exhaust or the bypass? Well, the bypass was needed. This was built for an automotive passenger vehicle application, where the concern was if you end up with a condition with very high mass flow, that you actually could get significant back pressure through the part. And this back pressure backs up on the engine and can actually cause the engine to perform at a poorer level than at a lower effectiveness, a lower efficiency. And so it's necessary for certain conditions to bypass some or all of the exhaust gas. This was also a way that if you had an over temperature condition, so as not to damage the thermoelectric material, that you could open up the bypass and bypass the exhaust gas. So one of the things too, and this was shown on one of the previous slides, these fins, we want to have as effective heat exchanger fins as possible. Therefore, we like copper. It has very high thermal conductivity. But putting exhaust gas through copper at 600 degrees Celsius is just going to destroy the copper. So we ended up using stainless clad copper. So we had 3/16 stainless steel fin that basically surrounded the copper in order to protect that. What surrounds this, so if you're looking at this outside, we then had rings, which I'll show on the next slide, which basically were put in contact with the outside of this heat exchanger. Here are the rings, and these rings were made of copper and had the thermoelectrics on one side. This represents the hot side of the parts. Again, now you can see closer up. This basically was the ring, and then here is one part of the thermoelectric material. Here's another part of the thermoelectric material, and then you had another connector here, which connects to the cold side, and it had a flexure in between that allowed again for some of the thermal expansion. If you imagine this part is getting up to 600 degrees Celsius, the whole thing expanded. And so in order to accommodate that, we built flexures into the parts themselves. This is another version of the cylindrical design that was built. And you can kind of see in this, where the TE elements were, how they were lined up on a connector, and then the coolant went through the tubes on either side of that. The elements we broke into. If I look at this device again, if I have my exhaust entering here, I don't want to have the same material at the hot end, and I'm extracting heat out of it continuously. And so I might want a different material at the hot end and a different material yet again in the middle, and yet then a lower temperature material on the cold end. So that's what we did. We ended up having relatively long segmented TE elements for the inlet region. And then we still had segmented elements, but they were shorter in size. And so they could handle the, and they also, the split in terms of the different materials were different lengths. And finally, at the exit region, we used just single material. This was bismuth telluride only, and both of the segmented materials in this case were Hafeussler on the hot side and bismuth telluride on the cold. This is some pictures of segmented parts. Ironically, these are not the segmented parts that were in the previous slide, but I thought I would show some examples of segmented parts, and these were made in different ways. This is a part that had lead telluride and bismuth telluride. In this particular case, they were soldered together. That's less than ideal because you build up contact resistance between these materials. And you really want to try to minimize the contact resistance as much as possible. That's not doing particularly any useful work for you. This was on the N side. On the P side of this part up here, we have bismuth telluride and tags on the hot side. And then in a separate effort, we had a three-stage segmented parts with scutteridite, tags, and bismuth telluride on the P side, and scutteridite, lead telluride, and bismuth telluride on the N side. These were not soldered together, these were pressed together. In sort of a second consolidation, the materials were consolidated initially and then went through a second pressing in order to make these parts. And then they were diced much like in the standard wafer. Sorry. Okay, one of the main things that I have done in my work in thermoelectrics has ended up being in modeling and simulations. So I show this initial slide just to show, again, here's our T-shaped design, but I was looking to be able to simulate how this would perform. In whatever material, I had to have temperature-dependent properties of the thermoelectric material. That can be shown here, where this, you have alpha for the Seebeck coefficient, kappa, which includes the thermal conductivity, and the electrical resistivity is in the R, and you still have interfacial resistance here. So these energy balance equations were basically set up in the simulation along the length of this generator. So I basically would set up one set of energy balance equations, then duplicate that throughout the, along the length, and then solve them simultaneously. So as it is, I'm going to show you guys a lot of different information here just on some of those results. This actually was just at a couple level, but it is showing that we were able to simulate, even at the couple level, segmented elements and their response in a dynamic fashion. I have steady state results as well, but I don't have that example here today. But you can see that the measured in the simulation, we're actually really able to capture quite well the time constants and the response. It's not perfect. You can see that here on the cold side temperature, but still you get the basic trend there, and that's still actually within a degree difference there. So I thought I would show you that. And then in so doing that, we also were able to simulate a drive cycle for a passenger vehicle. And in this case, we were able to input the temperature and mass flow information for such a drive cycle, and putting that with the TEG, we could simulate its performance. And you can see the power output. Well, first, I guess I should say the gas inlet temperature, which is in red, and you can see how much that still is varying. The gas mass flow rate is down here. There's also a tremendous amount of variation, again, in this application, and that causes the power output of the TEG to vary. Now this was again a simulated set. So, sorry. Okay.
So in this kind of convection, like what kind of heat transfer coefficient did you get?
So we tried to calculate what the heat transfer coefficient would be, and actually tried to use equations to figure out what that actually would get to. You used, well, and with gas, it's probably less than 1,000. As I think you used 300. That's probably not too bad for I don't remember specifically what the value was, and it was something that was actually calculated, so it wasn't a constant value. So we had a test bench to test this part. There's the tag that's under test. Here's the other tag here, just as an example. We had a blower. The gas heaters would go through here. The cooling system is actually not clear. It's not shown in this picture. Just wanted to show, we tested this under a variety of test conditions. So to make sure what's the robustness of the part, how well does our simulation actually predict performance across a range of conditions. In this case, we're talking about steady state conditions. There were 25 different conditions where the hot side, and this is in this case, the gas temperature was 620 degrees Celsius. Down to as low as 390 degrees Celsius. In this case, there was less variation on the coolant temperature. We used 40, we used 20. I'll now show you some of the results from those tests. So the dots are the actual test results. This is the power that was created. And the straight line, declining straight line, is the voltage. And the simulated results are actually the solid lines that go through those points. And you can see that we were able to really simulate and duplicate that performance. And I'm just showing a couple of examples here. This one at 620 C, this one at 510 C. And we're really able to capture what is going on from both a voltage and a power standpoint. We also were able to capture the airside pressure drop, and you can see the difference between the measured and simulated across the range of conditions that we were testing. The water outlet temperature, we had to be able to predict that. You have a certain inlet going in, but we wanted to make sure that we could simulate that as well. Wanted to measure the hot and cold temperatures of the shunts, or the electrical connectors on the parts. And you can see it's not perfect. This blue is higher than the red, but the general trend was captured there. And some of that variation too is getting thermocouples where you want them, what kind of even contact resistance you have between those thermocouples in the part that you're measuring. But you can see our level of being able to predict those temperatures, which after all, the performance of the generator is highly dependent on what those temperatures are. So our ability to predict that, and not only predict that, but be able to predict it along the whole length of the TEG. So we then, this model also was not only a steady state model, but we also had a transient aspect of this model too. And these models, by the way, were done in MATLAB. This transient part was done in Simulink. You can again see, so this is now at the full TEG level where we had changed some of the temperatures and the mass flow. And you can see then the response that we got from the TEG, as well as how well we were able to then model that. And so this is just showing some examples. We also had a changing electrical load in order to show how the TEG would respond to that as well. And then finally, just to show what the peak power that we were able to generate from this TEG was up to 700 watts. For the size, that was fairly significant. we were able to, that equated to 1,280 watts per kilogram of TE material used, and 49 watts per liter based on flange to flange dimension, including the outer shell and the internal bypass of the part. So from there, we then took this TEG and put it on to an engine, a dynamometer. And this is just showing some of the performance on that dynamometer, again, at now different conditions. This is all test data, no simulation data on here. And here we had a more dynamic set of conditions, again, still on that dynamometer. You can see how the variation in power output that we had, depending on whether that bypass was open, closed, what's the coolant temperature. So one thing you can see is there's a fairly significant impact of what the cold side is. We always think about the hot side temperature of these generators, but the cold side is in many ways even more important than the hot side, because if we look at the Carnot efficiency, which is delta T over the hot side temperature, you get a higher Carnot efficiency by reducing the cold side than you do by increasing the hot side. So, and in addition, we were still measuring some of those material surface temperatures, again, throughout the generator. And so we're just showing some of that response and our ability to measure that here on the hot side, as well as on the cold side. So these generators, there were two of them built. We were working with, at the time, Ford and BMW. This is the Ford integration, where you can see the generator here integrated into the bottom of the car, and the coolant lines and the bypass valve, the electrical connections. And then this is the BMW integration, where you can see the TEG with the exhaust line coming in. And again, these are the two vehicles that they were integrated on, and here is a set of test results for both of those vehicles. The BMW vehicle, we were able to get up to 450 watts of power. The Ford vehicle too, and you can see how, you know, the bypass was open, closed, and that caused some, in this case was closed. That's when the power shot up. The bypass was then, I'm sorry, the bypass was opened and then closed, and that changed the performance, of course, of the device. From BMW then was able to translate this performance, and one thing I haven't yet fully mentioned, but the one thing with this demonstration is that the electrical part of the TEG actually was not directly tied into the vehicle. This generator performed well, but it did have one major wart, that it operated at very high currents, the way that we had it built. Operated up to 500 amps and very low voltage, not very compatible with the electrical system for the vehicle. So some of the impact on fuel efficiency had to be calculated offline from that, and this is showing some of that as we see electrical power as a function of vehicle speed, and then the improvement in fuel efficiency, which the somewhat disappointing part of this, when you take into account all of the conversion and the effects on the engine due to the engine back pressure, etc., we ended up with a net of around 1 to 1.2% impact on fuel efficiency in this initial prototype. So I wanted to show that, and then we did have another version. So because of that very high current, low voltage, which was not something that was going to be very sustainable for in the vehicle, we had a next generation. Still a cylindrical type of device. We called this the cartridge. You still had rings with TE elements that surrounded the ring. You had P on one side of the ring and N on the other side of the ring. And then we made many of these cartridges, 18 cartridges would go into one generator. And you, again, you had a bypass here, you had exhaust gas that would go through these various cartridges. And in this case, the fins were surrounding the outside of the cartridge, and you had a coolant tube that ran through the center. You can see those tubes here. Yeah, so this too was built. I don't have the data from this right now, just for purposes of time, but I just thought I would show some of that. Moving away from the automotive tags, the other tags that were built, or at least studied, this actually is an example of a cartridge with a heat pipe that is replacing that coolant tube, and that would be another application of such a device. You could use a heat pipe. This would then be more of a regular flat thermoelectric module, and you have the hot side, and you then have the heat pipe on the cold side. Benefit of that is that no external power is required to move the working fluid, and again, it just contributes to the very low or no maintenance that's required for the parts. I'm kind of jumping back to some of the Alphabet Energy work. I talked earlier about the power cards that are shown here. There were two different setups. This power module I showed earlier went into the E1, which was used in, and I'll show actually on the next slide, where there were cold plates on both sides of it. There were many bolts. You can kind of see the bolt holes going through this in order to make sure that we had compression. We used Belleville washers as springs to kind of make sure that we had that compression. This was a design used for automotive again. And in this case, we were working with GM. And in this case, we have big springs that went on both sides. The power modules went inside here. And in between are the cold plates that we had. This generator was also integrated into a GM Suburban, and you can see the integration of that here. I mentioned the E1, 32 modules of those power modules comprised a single E1 system. This was for a 10 kilowatt system, and each of them had two cold plates on either side. In addition to that, we made something called what we call the power generating combustor. So if you've seen in the oil and gas fields, you have a flare that is often used to burn off excess gas. And this is wasteful, just waste heat that blows into the atmosphere. This was a way of basically, taking that wasted heat and using it to make useful power. So inside this power head, we again had multiple power modules, and this was able to produce 2.5 kilowatts off of a single flare. So I went through a lot. I also just wanted to touch again on some other opportunities. And again, this is far from exhaustive, and I don't have enough time to fully go through each and every one of them. You know, some of the things that we touched on, the gas flares I've mentioned. These are some examples of remote or wireless sensors from some US companies, Coherent or Marlowe and Perpetua. And you can see, for example, they're often linked to specifically the sensor, and you have this. This is the device where you have these parts sticking out, which basically is where you reject the waste heat to. And just this is an example of where some of those remote sensors can go. And you can see them in different examples on holding tanks, on oil production lines, on boilers, steam lines, etc. And I'm just going to end with, there's a lot of waste heat in the world, and these are actually only some of where you can recover that waste heat. I will say, although I don't have time to get into it fully, it is not always so easy to access and extract the waste heat from each of these types of applications. And so that is yet another part of that system design challenge, and it's part of the heat exchanger design. But there is a lot of waste heat in the world, and you know, thermoelectrics, I think, can help to extract some of it. Thank you.
Thank you.
Yeah, so we have 10 minutes for question and answers. If there are any questions, please ask. There is already one from the remote audience. Have you read that?
Sure.
Fernando Rivera, bismuth and tellurium are critical raw materials.
Yes.
Are there any alternative materials being investigated?
So yes. So, and I'll just go back to, I have looked at many different materials. This example is showing the bismuth and tellurium, bismuth telluride. And that is still the most prevalent thermoelectric material in the world today. It has both P and N type alternatives, which also makes it valuable. But it only really can effectively be used maybe to 300 degrees Celsius. Certainly not to 400, that's where it starts to decompose, but I have used it up to about 300 C. It's really most effective colder than that, and so that is an issue with bismuth telluride. Lead telluride, again, it's another material that has historically been used. Tags is made up of silver and germanium, and other materials that it's only a P-type material. Scutteridite is another material that has cobalt and antimony based, along with a variety of others. Tetrahedrite, which we're talking about here as part of this program, is another material that uses cobalt and antimony and sulfur. And magnesium silicide, I also mentioned before. So there are silicon germanium, there are many other materials. They all have sort of their niche. They all perform over best over different temperature ranges, which is yet another issue and challenge in thermoelectric waste heat recovery. Yeah.
Questions here? Yes.
Right. Yeah, very interesting. I really enjoyed that. I was wondering about the comment you made towards the end of your presentation, where you're fitting these devices in vehicles.
Yes.
And they obviously have to be custom made for each vehicle.
Eric?
Yeah. When can you get, or when will you be able to get this sort of off the shelf and not have to worry about and make it really cost efficient?
Well, unfortunately, that really was a challenge, and that this project this was reporting on an earlier project, and the cost effectiveness was a big part of why it didn't particularly go forward. I think there were a lot of technical successes that were approved in this program, but the cost effectiveness, the car companies are looking for a dollar per watt, or really less than that, and really they were looking for something as low as like 50 cents per watt. So that is a big challenge. But I would say that the majority of the car companies have looked at this technology over the last 10 to 20 years. Some more publicly than others, but they've looked at it and evaluated it. I think today, with a lot of things moving toward electric vehicles, that adds a whole nother part to that. Yeah. Unfortunately, I don't know that it's imminently going into production tomorrow.
Okay, thank you. You've said relatively little about tetrahedrites.
I have, and some of that is just based on a lot of the talks today, but this so this generator here, the automotive generator, used tetrahedrite. Alphabet Energy was in the process really of scaling up, and I started some of the slides showing us doing that, and we had developed the power card, but it was really still in a scale. We were still in that scale up mode. So there are tetrahedrite has its challenges with it too. I've mentioned the antimony sublimation and being able to try, and also preventing oxidation, needing to have a coating or something to prevent that. I would mention an alternative to having a coating in these parts. Actually, I'll just mention it here. In these cylindrical parts that were made at Gentherm, we didn't use a coating. We instead sealed the device in argon, as an example. So in an inert gas. So each of these cartridges, the thermoelectric material were sealed with an inert gas, and the larger cylindrical device had something similar to that. That may have been really challenging going into mass production that way, but that is what was done on these initial demonstration parts. But tetrahedrite would require some form of protection for that. There's also, temperature limitations. On the one hand, tetrahedrite certainly can be used to higher temperatures than bismuth telluride, but just as an example, you well know this, but much lower temperatures than silicon germanium. So you can't you can't just use it to however high a temperature as you want.
What is the temperature range that you have used?
That's still a little bit tricky. I still like to say, certainly less than 500 degrees Celsius on the hot side, and really a lot of times still under 400 degrees Celsius. It would be in that kind of range. Tags also had a limitation of about 400 degrees Celsius. Magnesium silicide somewhere in the 400 to 500 degrees Celsius. Lead telluride can be used to about 500 degrees Celsius. Scutteridite, there were different configurations of that could be used a little bit higher. Nothing as high as silicon germanium, which I have seen discussed use up to almost 1,000 degrees Celsius with some of the JPL's work in that area.
Yeah, it was quite an interesting device architecture with the T shape.
Yeah.
Why didn't you translate that also to the alphabet energy module?
Well, again, just because I had moved from Gentherm to Alphabet, there were other engineers as well, and also even some intellectual property relating to that design. And so went to trying to handle some of the thermal expansion differences with that flexible cold side. That is one of the challenges, particularly if you're looking at, say, tetrahedrite as a P-type material on the hot side, and something different on the N side is what those thermal expansion coefficients, how they differ between the two materials, how significant are those, and how much difference in movement are you going to have based on the temperatures. Just another one of those challenges, something that can be achieved, but overcome, but one of the challenges. Any other questions?
There are more questions from remote. We can take one, I think, because we are already a bit late. So maybe we pick Steve Casey, the first one. At Ultimate Energy, the latest TE materials used in the TE modules power cards were based upon tetrahydrates, correct?
Correct.
For high temperature use, 500 centigrades hot side and 100 centigrades cold side. What ZT was achieved for the TE modules power cards?
Yeah, and I don't have that specific information in the slides. The ZT, the peak ZT was less than 1, and particularly as we looked to scale up. So not just have what the hero material would be that you make in the lab, but as we were trying to scale that up, to be able to consistently have the same level of ZT was certainly another one of those challenges. And it was less than 1. I want to say it was in the 0.7 to 0.8 range for that in the scaled up fashion. But again, that was still at that development phase of things.
Okay, so thanks. Unfortunately, the time has run out. So thanks, Doug, again.
Yeah.
Maybe we can ask you the other questions that you can
Sure.
answer later.
Happy to. Thank you.
Okay.